Welcome back to another lesson on logarithms. Today we will learn some interesting properties of logarithms that will expand our toolbox for solving exponential and logarithmic equations. Let's get started. In this lesson, we'll look at 4 properties of logarithms. Even though the main goal of this lesson is for you to be able to apply the properties, we will learn these properties by first proving them so you can understand why they are true. Some of these proofs might seem odd or tricky, but all you need to do is let yourself go with the math flow. Let's discover our first property. Consider a product x times y, or just xy. Let's rewrite this entire product as a power of some base b. Applying our knowledge of logarithms, we know that xy is equal to b to the log base b of xy. Now, consider how, instead of rewriting the entire product as a single power of b, we could have rewritten x and y as separate powers of b. That is, b to the log base b of x times b to the log base b of y. Here we have a product of powers of the same base. Isn't there a property of exponents that would allow us to combine these? Yes, there is. The product property of exponents, which says that when we multiply powers of the same base, we add the exponents. Therefore, this product becomes b to the log base b of x plus log base b of y. It seems like we were able to write the same product xy as a power of b in 2 different ways. But since both powers are equal to xy, these exponents should be the exact same number. Therefore, it must be the case that log base b of x plus log base b of y equals log base b of x times y. We call this the product property of logarithms. Can you guess why we call it that? Because it was derived from the product property of exponents. This property tells us that when we add logarithms of the same base, we can combine the sum into a single logarithm by multiplying the arguments. Let's see this property in action. Let's rewrite log base 6 of 3 plus log base 6 of 8 as a single logarithm. How would you apply the product property of logs we just learned to this example? Since we have the same base, we simply need to multiply the arguments. Therefore, this sum is equal to log base 6 of 3 times 8, or just log base 6 of 24. On to the second property. Let's now consider a quotient x over y. Rewriting it as a power of b, we get b to the log base b of x over y. Once again, let's also rewrite x and y as separate powers of b. b to the log base b of x over b to the log base b of y. What property of exponents could we use to simplify this division? The quotient property of exponents says that when we divide powers of the same base, we subtract the exponents. Therefore, we get b to the log base b of x minus log base b of y. Since these 2 powers of b represent the exact same number x over y, these exponents must be equal. Log base b of x minus log base b of y equals log base b of x over y. What do you think we'll call this property? Since we derived it from the quotient property of exponents, we call this the quotient property of logarithms. And it tells us that when we subtract logarithms of the same base, we can write the difference as a single logarithm by dividing the arguments. Here's an example of how to apply this property. Log 35 minus log 7. How would you use the quotient property to simplify this expression? Both logarithms are base 10, so we can rewrite this difference as log of 35 divided by 7, or just log 5. For our third property, consider the expression x to the p. Rewriting this entire power in base b, we get b to the log base b of x to the p. Alternatively, though, we could just rewrite the x as a power of b. That is, b to the log base b of x to the power of p. I wonder what property of exponents we can use to simplify this power of a power. Well, the power of a power property. When we have a power of a power, we can multiply the exponents. So this expression simplifies to b to the p times log base b of x. Once again, since these exponents must be equal, we can say that log base b of x to the p equals p times log base b of x. We call this the power property of logarithms. One way to think about this property is that when you have an exponent inside the argument of a log, you can simply drop it in front of the log as a multiplier. Here's a quick example. Let's use this property to rewrite log base 9 of 8. But wait, this logarithm doesn't look like either side of the property. How can we apply it here? Well, we know 8 can be written as 2 cubed, and now our log looks like the left side of the property. Therefore, we can drop that 3 and multiply it in front, and we get 3 log base 9 of 2. Let's look at our fourth and final property. The proof of this one is a bit trickier, so make sure you follow along. Consider some logarithm base b of x. Now, let's rewrite the argument x as a power of some other number y. Since we have an exponent here in the argument, we can use the power property of logarithms we just learned and drop the exponent in front as a multiplier. We just showed log base b of x equals log base y of x times log base b of y. Lastly, let's isolate log base y of x by dividing log base b of y on both sides, and we get that log base b of x over log base b of y equals log base y of x. We call this the change of base formula. What is this formula saying? It says that when we have a ratio of logarithms of the same base, we can combine these into a single logarithm, whose base is the argument of the denominator, and whose argument is the argument of the numerator. However, we often present this formula in the other direction because, as the name suggests, we often use it to change the base y of any logarithm into whatever base b we want. Let's see how that works with the following example. Let's rewrite log base 7 of 8 in base e and find its decimal approximation. As we know, logarithms base e are natural logarithms. Therefore, according to our formula, log base 7 of 8 should be equal to ln 8 over ln 7. Since 7 was our original base, it becomes the argument of the denominator, and since 8 was our original argument, it becomes the argument of the numerator. Putting this in a calculator, we'd get around 1.0686. Why would it ever be useful to change the base of a logarithm like this? Well, if you only had access to a scientific calculator and not to a graphing one, chances are it would not be able to calculate a logarithm base 7 like this one. Scientific calculators usually allow only two types of logarithms, base e and base 10. With the change of base formula, you can turn whatever logarithm you need into a ratio of natural or common logarithms that your calculator can process. Here are all the properties we just learned. Make sure to have them recorded in your guided notes. Let's use these properties to solve a couple more problems. Now it's your turn. Here's example 5, which you'll find in your guided notes. Pause the video and simplify these logarithmic expressions by applying the properties we learned. First, we have a sum of logarithms with the same base, so by the product property of logarithms, we multiply the arguments 12 and 3 and get log base 6 of 36, which we can actually just evaluate ourselves. Since 6 squared is 36, log base 6 of 36 is 2. Notice how we couldn't evaluate log base 6 of 12 and log base 6 of 3 separately without a calculator since they are irrational. But when we combined them, the result was a nice logarithm we could easily evaluate. Next up, log base 5 of 4 minus log base 5 of 100. According to the quotient property of logs, since we have a difference of logarithms with the same base, we just divide the arguments, and the result is log base 5 of 4 over 100, which simplifies to 1 over 25. Do we know the value of this logarithm? Yes, 5 to the negative 2 is 1 over 25, so log base 5 of 1 over 25 is negative 2. Then we have 2 log base 4 of 8. Here we can use the power property of logs in reverse. We can bring up that 2 as an exponent of the argument, and by doing so, we will get log base 4 of 8 squared, or log base 4 of 64. Once again, we can evaluate this ourselves. 4 cubed is 64, so log base 4 of 64 is 3. To wrap up our lesson, let's see how these properties allow us to solve a more complex exponential equation. 3 to the 2 plus x equals 4 to the x. How is this equation different from the other exponential equations we've done in this unit? This equation has variable exponents on both sides. In our last lesson, we saw how we can solve exponential equations by taking the logarithm of both sides in order to undo exponentiation. Could we use this same strategy here? We run into a little dilemma. We have exponentiation with base 3 and with base 4. Which one do we undo? Let's see how taking logarithms base 3 would play out. Even though we'd only accomplish undoing the exponentiation on the left side, the fact that 4 to the x ended up inside a logarithm is enough to help us release the x. Can you see why? Because of the power property. We can drop the x in front to multiply, and now we have all our x's down. This equation looks kind of weird though because of that logarithm, right? Remember, log base 3 of 4 is simply some irrational number that we can't write out as an exact decimal, like pi. Even though it might not look like it, this is actually just a linear equation where the x's have coefficients 1 and log base 3 of 4. We simply choose to write logs after the x's so that it doesn't look like the x is part of the log's argument. How would you start solving for x here? We would need to subtract 1x, or x, on both sides. Now, we could put log base 3 of 4 minus 1 in the calculator and get an approximation, but then we wouldn't end up with an exact solution to the equation. To keep the exactness, we can instead literally just write log base 3 of 4 minus 1 and the x on the side. If we want to remind ourselves the 4 and the 1 cannot be combined because the 4 is inside the logarithm, we can put the 4 in parentheses. Also, remember, we prefer our x's in front of the logs. Lastly, we divide by log base 3 of 4 minus 1 on both sides, and we get x equals 2 over log base 3 of 4 minus 1. At the start of the problem, we were wondering if we had to use log base 3 or log base 4 to solve this equation. How do you think it would have played out if we had chosen base 4 instead? On the right side, we would have released the x by undoing exponentiation, and on the left side, we would have dropped the x thanks to the power property. After that, we would have been able to isolate x. It seems like the reason both approaches work is that the power property allows us to drop the x's even when the log and the powers have different bases. However, doesn't the power property work with logarithms of all bases? Couldn't we have solved this equation then with logarithms of any possible base? Actually, yes. Since literally any log will work, we often stick to solving with our favorite logs, the natural logarithm and the common logarithm. Try to solve this same equation, but now using natural logarithms. Here's the first step. Pause the video now and give it a shot. First, we drop the exponents and get 2 plus x times ln 3 equals x ln 4. On the left side, we have the number ln 3 multiplying a binomial, so we can apply the distributive property and we get 2 ln 3 plus x ln 3. Then, we subtract x ln 3 on both sides and combine like terms. Since we have same base logarithms on the right side, we can divide arguments and combine them as x ln of 4/3. We divide both sides by ln of 4/3 and we get 2 ln 3 over ln of 4/3. We can make this answer look a bit nicer by raising that 2 as an exponent of the 3, which gives us ln 9 over ln of 4/3. While this answer is fully correct, we could make our answer even more compact by using the change of base formula and writing log base 4/3 of 9. But wait a minute, we got a different answer than before. What happened? Well, it turns out we can use properties of logarithms to prove these two solutions are the same. In your guided notes, you have a bonus problem after this example where you can try this out yourself. Here's a hint to get you started. Begin with log base 4/3 of 9 and rewrite it using the change of base formula. Then, work your way toward 2 over log base 3 of 4 minus 1. In this lesson, we learned these 4 properties of logarithms, which allowed us to not only simplify and expand logarithmic functions, but also solve a greater variety of exponential equations. In our next lesson, we'll learn one last pair of strategies that will help us solve an even greater variety of exponential and logarithmic equations. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time! Hey, hey.